are going to be continuing our talk of Newton's laws. We talked about Newton's first two laws last class period. I'm going to review them here real quickly because they're super important. Like among the things that are most important for you to learn, most important thing is going to be that scientific method. And then Newton's laws here, probably the second most important thing in this class. So the first law, also known as the law of inertia, is the law that says that an object in motion stays in motion unless acted on by a net external force. So the wording, you'll read different wording different places, but uniform motion means constant velocity. Of course, velocity has two pieces. What are the two pieces to velocity? Direction and speed. So constant speed and constant direction unless a force acts on it. So you can take something like a car turning, its direction is changing, hence it has to have a force to make it turn. A car speeding up, to change its speed, has to have force to make it speed up or slow down. So the first law just says things will travel at a constant velocity unless something makes them change. Remember, that's different from Aristotle, who said they naturally just want to be at rest. The second law is the one that gives us the equation. It relates the acceleration to the force applied to an object and the mass in the object. So we can write this equation or this law very simply as an equation that says the net force is equal to mass times acceleration. Acceleration and force are vectors, so I put the vector signs on those. The net force, what does net force mean? The total. When I add everything together. Another way of writing net force that I showed you last class period is like this. That capital sigma means sum. Sigma being Greek S. So Newton's second law allows us to relate how something is going to respond to a force. In fact, I think the preferred way of writing this in our textbook is to write it as the acceleration is equal to the net force divided by the mass. So this picture shows some simple examples. So I will do a variation of those simple examples. Is the screen blink or am I going crazy? I'm going crazy? Thanks. Okay, so I have two things here. The tennis ball and the 500 gram mass. They don't have the same mass. Which one do you suppose has more mass? 500 gram one has more mass. Now I will go to Tyler here just so he can verify. Now how does he determine this one has more mass? By actually judging his weight. He can't really judge the mass by what he did. He could have judged the mass. He could have gone like, it was easier to throw the punch with the ball than with the mass. Because then you're applying a force and seeing how easily it moves. But what he did was just go like this. He was measuring the weight, measuring how much force he had to apply to just keep it still. And in that case, gravity, the force of gravity, is proportional to the mass. And so he said, well, the one that has the higher force of gravity has the higher mass. If you've never had physics before, that thought process certainly wouldn't be the one that went through your head. But you still would have the ideas in your head. Because things like, the idea of mass, a lot of people don't think about the idea, but they still have the concept, more of this, less of that. Okay, so he determined this one has more mass. The example there is just a grosser exaggeration of this. I have two things are circular, this should roll, right? If I flick them both with my finger, I'll give them about the same force. Are they going to roll about the same amount? It's going to happen. The what? Okay, the tennis ball is going to go faster and farther, so it's going to hurt my finger too. There we have it. And yes, it hurt my finger. So you can see the difference. This here is an idea that is actually pretty brilliant when you think about it. If you have a baseball bat and somebody pitches a baseball at you, you're not worried at all about hitting that ball. You'll swing away and crush it, right? But if you've got a baseball bat and somebody pitches a bowling ball at you, we pretty much, everyone who's ever hit something like been mad and hit a post with a baseball bat, you realize that's a bad idea. Right? Because when you hit that bowling ball, it's not going to bounce off of your bat. It's just going to try to go through. It's going to take a whole lot more force to make the bowling ball stop and go the other direction. And that force has to come from your hands. Yeah. You wouldn't want to do that. So, let's move forward. And I think I got a clicker question. Nope, not yet. After this. So just a few more statements about Newton's second law. I think we've talked about the units of force from Friday. Units of force are the Newton, named after Sir Isaac Newton. And if you work out the math like we did on Friday, mass times acceleration has units of kilograms times meters per second squared. So the unit of force, the Newton, is a kilogram meter per second squared. This name inertia is given to just the state of nature that things tend to stay in constant motion. So inertia, the law of inertia being the first law, inertia is just a propensity to stay in constant motion that is in contradiction to what Aristotle had thought, that things just wanted to be at rest. So we have that idea of inertia, and inertia is actually measured with mass. The more mass something has, the more it simply naturally stays in constant motion. Okay, now our first clicker question, which is, did you pay attention to a few things? In Newton's second law, the F and A are in bold font in your textbook. Obviously, when I write them down, they're not in bold font. But the M is not. What does this tell you about M? Okay, everyone's answered. We had 1, 0, 6, 0, 3. So, one person said, it tells me nothing. I'm hoping that person was just being honest, that they didn't understand. It does have a significance, but if you don't understand it, then it does indeed tell you nothing. Which is why I ask these questions, to make sure that we can reinforce or make sure people understand. Okay, there was no one who said M has direction but F and A do not. There was no one who said M is not as important as F and A. I am glad no one said those. Those were clearly incorrect. So the other two, one is that M is smaller magnitude than F and A, and one is M has no direction. The correct answer, dun dun dun, is this. In your textbook, or when you read other books, bold is very commonly used to indicate a vector. And so the fact that F and A are bold means they're vectors. Whereas M not being bold means that it is a scalar. It has no direction. Now when I write these, instead of putting the bolds, what do? I use the arrows. So you have to have the recognition. Sometimes you'll see with the arrows, and that means vector. Sometimes you'll see with the bold, and that means vector. Right? That's, like I said, the first lecture. Kind of a different language we use when we're writing equations. And so part of the difficulty is learning this new language for the way we write our equations in math. Okay, a little example. I have an object. Here's an object. Now I don't have a string tied to this, so instead of pulling a string, I'm just going to push on one direction, or one side. I push, and it moves, right? In terms of Newton, why did it move when I pushed it? Because of what? Because of the force you applied. Okay, I applied a force, and Newton's law tells us how something responds to forces. Now, this problem shows two different forces acting in the horizontal direction of the block. Now, we talked about motion, right? I threw the ball many times at Denford. I got it to him about once. When we talked about that motion, what did I say about the way you can treat the motion in the horizontal direction compared to the vertical direction?
No force of gravity on the horizontal.
Okay, I have no force of gravity in the horizontal, only in the vertical. And I could then solve the horizontal problem completely independently from the vertical problem. And the same is true when we talk about these force problems. So this only shows horizontal forces. We know that gravity is a vertical force. There is a force of gravity on this box that is pushing it down. And the force of gravity has an equation mg. And I will actually, in just a few moments, work out to show you a simple explanation of why it's mg. So we have this force of gravity pushing down. Is that box accelerating downward right now? No, it's not. If it's not accelerating downward, what does that tell you about the sum of the forces in the downward direction? Remember I said we can treat the directions independently, so I'm just looking at downward. What does the sum of the forces have to equal? Okay, the sum of the forces has to equal 0 because sum of the forces is mass times acceleration. So if the vertical acceleration is 0, then the forces in the vertical direction have to be 0. Well, I've got that force down, so if the sum of the forces is 0, how can I have a downward force and have it add up to 0?
Surface.
Okay? I have to have a force pushing up from the surface. So I have to have a force like this, and the name we give it is the normal force. Normal because that means it's coming out of the surface in the direction that has the name normal. The normal means the direction is coming out of the surface perpendicular to any line you can draw on the surface. So I know the force normal, the normal force, must equal the force of gravity in this case, so the net force is 0 in the vertical. Now if we switch to the horizontal, I have a force of 10 newtons to the right and 2 newtons to the left. Now Newton's second law says the sum of the forces, so if I have 10, I'll use my left hand, it just feels awful, 10 to the right and 2 to the left, what's the total of those? It's 8. Now, some people might say, okay, so is teacher gone bonkers? 10 plus 2 tends to be 12. But no, it's 8. Why was it 8, Denford?
Because one of the forces is going in the
Right, because one is the negative direction. And so they add up to 8. So now I can just take Newton's second law. The acceleration is the net force, my 8 newtons, divided by the mass. When you do the net force, you actually always have to be careful. It's the net force acting on the object you're interested in. Not just all of the forces anywhere. Only the ones acting on the object you're interested in. So I took that net force acting on the object I'm interested in the horizontal direction, 8 newtons, divided by the mass of the object that had those forces, and that gives me the acceleration of that object. So Newton's second law applies to an object. Now that object could be a complicated object. It could be something like, my car and everything in it. Or it could be a simple object like, this ball. But you take all of the forces acting on that object, the mass of that object, and you get the acceleration of that object. So 8 divided by 5. 5 divided by 5 is 1. That leaves a remainder of 3. 3 divided by 5 is 0.6. 1.6. Okay, so another clicker question. Two equal magnitude horizontal forces act on a box. And if you look at the picture, it doesn't say this in the words, but in the picture you see the directions. Is the object accelerated horizontally? Dos más. Uno más. Done. Excellent. Everybody said no, it doesn't accelerate. So since you all said no, it doesn't accelerate, I should be able to ask anyone and they'll give me the right answer, right? So, Colby, why is the answer no?
Because the forces cancel each other out.
Okay, the forces add up to 0. I reserve the word cancel for when you divide and get 1. That's why I changed your wording. I know what you mean. Okay, so that was simple enough. Now, what can you tell me about the speed of this object? Okay. Bronco fan shrugs his shoulders. It's a good sign. You can't tell anything about the speed. A lot of times we tend to think, oh, it should be at rest. After all, I used the example of that block, and that block is at rest. But Newton's second law only has to do with the acceleration, with the change in velocity, not with the actual velocity. So it could be at rest or it could be moving. It just has to be at a constant speed and a constant direction. So it can be moving at a constant speed. Example, there, the box is moving at constant speed. So I get to where I have to stop. Moving constant speed. Am I pushing on the block? Yes. If it's a constant speed, what is the acceleration? And if the acceleration is 0, what's the net force? And hence, since I was pushing to your right, what do you know had to be occurring as well? There had to be a force pushing against me that we call friction. And that was the thing that Aristotle didn't understand with his idea that things just have a natural propensity to come to rest. That Galileo said, yes, there's a force that's acting there that's opposing it. Okay, follow-up question. Is it possible... I forgot I had this as a follow-up question, or I would not have just asked you this question without doing the clicker. Is it possible that the box is moving since the forces are equal in size but opposite in direction? Okay. We actually ended up 8-2. That was because Colby was actually playing with me, making the wrong answer. Okay. Is it possible that the box is moving? If the net force is 0, what does that tell you? No acceleration. Doesn't tell you what the velocity is. So it's perfectly possible that that ball could be moved, or that box can be moving. It just would have to be moving at a constant velocity. That is a constant speed and a constant direction. Okay, now we take a third and final look at this problem. We still have two equal forces, but now one is horizontal and one is vertical. If these are the only forces involved, so there's no gravity, no forces normal or anything like that, will the object be accelerated? All right. Pretty much the same spread we had last slide. I'm right on top of things. So 8 people said, yes, it'll be accelerated. 2 said no. Now, the 8 people are correct, but for the benefit of the 2, I'm still giving the rationale here. Newton's second law says that the acceleration is equal to the net force divided by the mass. So I look at these 2 forces. I have a force that's to the left and a force, or to the right, excuse me. I've been looking at things backward because, yeah. If I add those up, those are not going to add up to 0. And in fact, I know what they're going to add up to, because when you add vectors, you add them tip to tail. And so this is going to come up here. So it goes over as far as F2 did and as high as F1 did. And that is going to be my net force. So if that's my net force, that's not 0. Since it's not 0, it must accelerate. And what direction is it going to accelerate? Yeah, the direction of that arrow. Now, I could have asked you about its horizontal acceleration. Will it accelerate horizontally? Yes, because it has a component, a piece of the force that's horizontal. Will it accelerate vertically? Yes, because it has a piece that's vertical. And so you put those together and it's going to shoot off in the direction of that arrow. Man, I have more clicker questions today. This brings forth a whole good set of problems that almost certainly one of these elevator problems will show up on your test. They're very ubiquitous. You're in an elevator that's accelerating downward. What forces are acting on you? Oh, by the way, you have to put in all the answers you believe are correct and then hit enter. Because of the having to hit enter part, just make sure, Andrew, you're still, there we go. Okay, so everybody's entered. Here are the answers we had. All but one person said the force of acceleration. 5 people said force normal. 8 people said the force of gravity. 7 people said the force of friction. And 7 people said the force of speed. I would have you discuss this, but I don't think that it would help very much. There's a very broad spectrum here of answers. So what was the point of this question? Right? Certainly I don't grade you on the correctness of these answers. It's for learning. And the point was to help us identify forces. So at this point, the forces we've talked about are friction, gravity, and normal. Of the forces shown up there, those are the only ones that actually exist. There is no such thing as the force of acceleration. You have acceleration that occurs as a result of a force, but you don't have a force of acceleration. Likewise, there is no force of speed. I can't think of a way that I could even come close to trying to describe what a force of speed would be. But that may be because I'm so indoctrinated into physics that I'm not thinking. Because clearly 7 people thought that made sense. So forces are anything that push or pull. And so basically you have to ask yourself, does speed push or pull on me? The speed itself doesn't. Does acceleration push or pull on me? The acceleration itself doesn't. It's a force pushing on you that makes you accelerate. Force normal, of course, force normal is a more complicated idea because force normal means the force normal to a surface. So you have to ask, does this surface put a force on me? And yes, right now the ground is putting a force on me. If I were to run and clip the edge of the table, that edge of the table would definitely put a force on my thigh. So that would also be a force normal when I hit the table. Because I'd be hitting it, be putting a force directly into me from the table. Force of friction. Forces of friction are a little more complicated. We're going to talk about those a little more later. But forces of friction, if I was, some ballerina who was perfectly balanced on my toes, well, I'd be real trouble. Anyway, if you're only moving in a vertical direction with no horizontal motion, then there's no friction. If there's even the slightest horizontal motion, then there's friction. So let's put it in a simple fashion. I can stand here like this quite nicely. The net force of friction on me is 0. That is if I add up the forces of friction. This foot here has friction that's pushing it in. That one there has friction pushing it in. Those add up to 0. So as long as I'm standing here stationary, the net force of friction is going to be 0. But of course, there is a force of friction acting, one on each foot. What would happen if there was no force of friction? Yes. Me not being one of those crazy dancer types, I would just fall down. I would go, boop. My legs would go out. It would hurt a whole lot. Now you see these crazy people on, so you think you can dance with those other students. Okay, I don't like those guys. They're fairly worthless. But you see these people who can actually go slowly down into the split and then stand back up. Okay, that's taking a lot of strength. A lot of strength. It's a whole lot of force you have to apply to make your legs do that. That's, you can do that if there's no friction. So they're working with a low friction thing, probably in their shoes, put it on the side or something so that it doesn't grip very much. And if there's no friction, I would just do the down part and never come back up. If there was no friction, likewise, if I'm in the elevator and I'm trying to move to the side of the elevator and there's no friction, I'll just fall down. If there is friction, I can move to the side. In the traditional elevator problem, we're restricting ourselves to just standing stationary in the elevator. And the elevator is moving vertically, so there is no side-to-side motion. Hence, we say that the friction force is 0. Now, that was a lot of description for why we say the friction force is 0, because I want you to understand that wasn't necessarily a wrong answer. If there was no friction, even just keeping my feet 6 inches apart, I would have to be doing a little bit to keep my feet from sliding in and out, right? And I always have a little bit of friction I'm relying on, but it's a little bit, and so that's why we just say, okay. It's not necessary if instead of being humans on feet, we were blocks. If you had a block and it's all moving vertically, you wouldn't need it. So the correct answers here were, don't need the force of friction, you need the force normal pushing up, and you can't help it, you have the force of gravity pushing down. Now let's look at a picture of a person in an elevator and what the traditional problems are. So here we have a picture of a person in an elevator. I sure hope that I gave you a problem like this on the homework. I haven't looked at it since the first week of the semester, so I can't remember. You have the person in the elevator has to have the force normal to keep him or her from falling through the bottom of the elevator, because you have the force of gravity pushing down. Now this picture is very busy because it's showing a lot of forces on the right-hand side. You have a force of tension of the rope pulling up on the elevator. And of course, it's really not a rope, it's a cable. Okay. So you have that force pulling up in the elevator. You have, in this case, the guy standing on a scale, and so you have the force of the guy pushing down the scale, and you have the force normal acting on the gentleman, is the force of the scale pushing up on him, labeled there as Fs. Then you have the force of the floor holding up the scale, the force of the scale pushing down the floor. A lot of forces there. Why would they put so many forces? Because this picture is here to illustrate a lot of physics ideas. And one of those ideas is the one that Newton's second law is the sum of the forces on an object is equal to the mass of that object multiplied by the acceleration of that object. Now, you'll never see me write it like that again. You'll never see it written like that. Nobody does. But it's important to understand in Newton's second law, all of those are applying to the same object. So when you look at this dude in the elevator, the first question you have to ask yourself is, what is the object I'm looking at? So now, it depends on your problem what you're going to be looking at. Let us suppose the problem asks us, what does the scale read? That makes it so I can identify the object I want to look at. But the object I want to look at is probably not the one you think it is. If I want to know what the scale reads, I first should maybe be clear on what a scale reads. When you stand on a scale, what does it read? Okay, it reads the weight of what?
Gravity.
Well, the weight of what object? The weight of the person that's standing on the scale. Not the scale's weight itself. It's measuring the weight of the person standing on it. So if I stand on a scale, I am pushing down on that scale. Now, Newton's third law, I haven't come to the slide on Newton's third law yet, but I really need to have it now to explain this thoroughly. Newton's third law, everybody has heard. For every action, there's an equal and opposite reaction. In that statement, action means force. And reaction means a returning force. So Newton's third law says for every force, there's an equal and opposite force. So if I push down on the table, I apply the force to the table. That's a force acting on what object? It's acting on the table by me. It's a force between two things. Newton's third law says that there must be an equal force, but in the opposite direction, acting the other way. So this was a force, me acting on the table. There has to be one of the table acting on me that's exactly the same, but in the opposite direction. If you look at the case of the scale, the man is standing on the scale and he's pushing down on the scale. And so the scale, according to Newton's third law, is going to push up on him with a force exactly equal to the force the man's pushing down the scale. And the force we're looking for is that force of the scale is pushing on the man, because that's what it reads. And so, since I'm looking for the force that the scale is pushing on the man, there are two choices I could make for the object. First, there's the wrong one. The scale is the wrong one. Why is the scale the wrong one? Because I don't have enough information if I just do the scale. The second one is the right one, the man. If I choose my object to be the man, then I know the other forces acting on him. On the man I have, that's I can get numerical values for it. I have the man has a weight that's the force of gravity. And so the man has, acting on him, a force of gravity, called the weight here, that's pushing down. And he has the force of the scale pushing up. So it's just two forces that are acting on the man, and one of them is the one I want to find. That force of the scale, what have we been calling it before this? The force to keep him from going through the scale? The normal force. So we've been calling that the normal force. Now we're calling it the force of the scale because there's more than one force normal in this problem. And so you have to be, you get to name your forces. you have to make sure you choose names or you'll be able to identify them. So as long as you know what the force names mean, you're going to be good. So there's only 2 forces acting on the guy. Well, that's good. We can work with 2 forces a lot better than we can work with 7 or 8. This picture over here is called a free body diagram. And what that has done is it has taken the object that we're looking at, in this case the man, and said, okay, this dot is the object. And now I'm going to draw all the forces that are acting on the object. So from all of the forces in the picture on your left, only the forces that are acting specifically on the man, not forces of the man acting on something else, but the forces of other things acting on the man, are shown there. So there's only 2 forces acting on the man, and they're shown. In our physics problems, we make these free body diagrams all the time. Why? Because it makes it easy for us to apply Newton's second law. The whole point of the free body diagram is for using it with Newton's second law. So now with this picture, I can say the sum of the forces on the man, I dropped the vector sign because they're all in one direction. They're all in the y direction. So this is just going to be a y direction problem. Notice this here is what told me that y was vertical. So the sum of the forces in the y direction on the man is equal to, and then I just look at that free body diagram. Since my direction arrows show y pointing up, the force that's pointing up will be considered positive. So which one should I consider positive? Which one? Okay, can you read the names or are they too small? Okay, there you can read the names. Which one is going to be positive of those 2 forces? I'm going to get my hearing check yet again. F sub S, right?
Yeah.
Yes. The force from the scale. So this one here is pointing up. It's going to be positive. They call this weight. I far prefer to call it force of gravity. Is pointing down. That's the opposite direction of up, and hence negative. So I'm going to have the force of the scale minus the force of gravity is equal to mass times acceleration. Now this brings up something interesting. The force of the scale is equal to force of gravity plus mass times acceleration. If the elevator is accelerating upward, would that be a positive or a negative acceleration by the definition of y? It would be positive. So if A is positive, if the elevator is accelerating upward, what does that tell you the scale is going to read? It's going to what? Heavier. It's going to read his weight, the force of gravity, plus his mass times the acceleration of the scale. Or of the scale, of the elevator. So if the elevator accelerates upward, the scale will read heavier. Well, God forbid. I always want to be in the elevator with it accelerating downward, because if the acceleration is downward, then A is negative, and what is the scale going to read? Lower. So as long as I put a scale under me, and I only measure the acceleration or measure my weight when the acceleration is downward, it'll tell me I'm lighter, and I'll feel good about myself, because clearly I'm more than I should be. So now let's think about when that occurs. Let us say that an elevator goes between the basement to 7th floor of a building. And so here I'm going to have elevation and floors and time on this axis. So I have position on the vertical axis, time on the horizontal axis, and the elevator does something like this. It starts in the 1st floor, goes down to the basement, stops in the basement. Actually, I need to make it so it doesn't travel quite so fast.
gets to the basement, picks up a load of people because worship was in the basement. Then it goes up. Actually, no, worship was on the first floor. It was the TV room that was in the basement. Goes up to the 7th floor and dumps everybody off. So in this picture, when was the elevator accelerating downward? What'd you say, Rachel? Not exactly. It was accelerating downward here when the slope was changing. And then again at the top when the slope was changing there. What about the acceleration the other two places where the slope was changing? What's the acceleration here and here? It's upward. So if you were to plot acceleration on the same time axis, the acceleration is 0 when it's stationary. When it starts going down, it's going to go down, and then comes back up, gets to the bottom, goes up to make it stop, comes back down, goes up to make it start going back up again, gets to the top, and goes down to make it stop again. So showing what's supposed to match up in time, just because my artistry is not perfect. So I can look at that bottom graph. If I'm in between floors moving at a constant velocity, my acceleration is 0. What does the scale read? The acceleration is 0. What is the scale going to read? It's going to read just my weight. Yeah, you're all like, I don't want to say what his weight is. It's going to make up a ludicrous weight, but then you might believe me. Okay, let's go to a related topic and then come back to this. A related topic. I have a ball. A ball. I let go of said ball. What's it going to do? Accelerates downward. It falls. Why does it do that? Gravity. Now, with our approximations for this class, there is no air resistance. Certainly, we're not going to consider any buoyancy. So, if I let go of that ball, what forces are acting on it once I have let go? Just gravity. So, when I let go of that ball, the only force acting on it is going to be the force of gravity. How do I know it's down? Because we define down as the direction of gravity. Okay. According to Newton's second law, the sum of the forces is equal to the mass times the acceleration. Looking at my picture, sum of the forces is going to be force of gravity in the downward direction, so I'm going to put a minus there. Minus for the direction. Equals mass times. What's the acceleration of the ball if I drop it? Yeah, it's what we call g, 9.80 meters per second squared. In what direction? Down. So minus for the direction, and then we just use g, and I'll write over here, g, the 3 lines mean is defined as And so I look at this, and there's one more step that is so simple you probably don't think there's a step left. Multiply both sides by -1. And what that tells me is the force of gravity must equal mg. Is that the simplest explanation you can think of for why the force of gravity has the equation mg? It's just applying Newton's second law and taking what we have already seen, that the acceleration is constant, and we give it the symbol g. I say we've already seen, you're going to see that some more in lab today. So the force of gravity has an equation mg. Now let's go back up to our problem with the elevator. We had the force measured by the scale is equal to the force of gravity plus ma. making the substitution that force of gravity is mg. That's equal to mg plus ma. Or you can factor out the m. Since they both have the m, I can say that's m times g plus a. And so the force to scale reads, if you're going to be calculating, it's usually easier to put it into this form because you have different accelerations and you just do a little piece multiple times. But it's interesting to me, the force of the scale is proportional to the mass. And so if a Bronco fan and a Raider fan are on the same elevator, and it happens to be me and Tyler, as we go down, the forces that the scale would read to me are going to swing by much bigger values than they would swing for Tyler, because my mass is much bigger than Tyler's. But proportionally, that's as a percentage, the swings would be the same, because it's just proportional to our mass. We got 3 minutes left, and I am halfway through the slides. That probably means that we're not going to get all the way through. So we've shown you how mass and weight relate with that ball dropping thing. The weight is the force of gravity, mg. Depends on mass because, well, I just said it. Weight, mg. However, if you are in the International Space Station, we would say that you are weightless. Which means mg is 0, right? Actually turns out to be different. It's the definition of weightless varies depending on who you are and what you're talking about. If you're in the International Space Station, believe it or not, the acceleration of gravity at the International Space Station, you guys know what I'm talking about, the International Space Station, orbiting around the Earth. The acceleration of gravity there is somewhere between 80 and 90% what the acceleration of gravity is here on Earth. And so one would say, well, their G is 80, 90% what it is on Earth, so their weight should be 80, 90% of what it is on Earth. But we say they're weightless, which implies 0. How does that work out? Because the International Space Station is falling toward the Earth, and so are they. And they're falling at the same acceleration as the International Space Station, so they say, I'm weightless because I can put a scale here, I can stand on the scale doesn't even have to be sitting on the floor. And it's not going to measure anything unless I'm moving or if it's on the floor and I jump off. So we say they're weightless. They feel truly weightless. Of course, we can do the same thing on Earth then. We could put you in an elevator, in a nice elevator shaft with all of the air sucked out below so it won't stop you. And we just disable the brakes and cut the line, much like in speed. And then you fall, and the acceleration of the elevator is going to be g. And your acceleration is going to be g. And so you'll be in the elevator and you'll be like, I'm floating, woo! Until something amazingly bad happens, the elevator stops. When the elevator stops, what happens to you? Yeah, you have a lot of momentum, as we say. You've been moving pretty fast, and now you're going to stop really quickly. What does that mean about your acceleration if you stop really quickly? It's going to be a very large acceleration, which means that the force necessary to cause that acceleration is very, very large, and hence you flatten out. When I was in grad school, the students a year behind me thought it was hilarious to get on the elevator and lie down, and then when the elevator stopped at the bottom floor, they'd all bang the floor with their arms, and then the elevator doors would open, they'd be all laying on the floor. Like there had been some disaster. They were a year behind me. They were young and immature. Just one last thing to end the lecture. When you watch movies and you have something like a person is plummeting off the building and, oh no, what will I do? And somebody like, oh, let's take TV show The Flash. The Flash runs and catches them and takes them back up to the top of the building. And everything is fine. Disaster averted. That's not what physics says would happen. What would happen? Yeah, the Flash just broke them in half. Right? The Flash would not be saving anyone's life. He would be killing everyone that he helps. Okay? Just to put these things in perspective. Just because you don't hit the ground doesn't make the acceleration less. In fact, in many cases, it's going to be more. And that's bad. All right. Have a great day. We may or may not have school tomorrow, but we will have lab this afternoon.